These are in your book, and I can give you a reference so you don't have to worry about them. What I'm showing you is actually on page 450 and 451 in some way, shape, or form, but I want to put this up here where I like to do it. Sorry, I want to get these down. This is all in your book in some form, but I want to refer to them, and I don't want to spend a lot of time doing this and interrupting the lecture, so just hang on. All right. I'll get out of the way. Go ahead. By the way, thank you again for taking notes. Did you post the last set of notes? All right. Is everybody seeing the notes that she's posting back there? Thank you very much for doing this. It helps everybody, I think, including me. And the reason I put this up there is really for your benefit. You took a picture of it, and I'm glad. If anybody, you got a good picture of that.
Yeah,
right?
thank you.
Let me go through this with you. This is an arbitrarily long dipole, not short. Now, I used to go through the proof on this. I can, but I'll just talk my way through it and explain this. Normally, if we wanted to calculate that electric field from this dipole, what we do is we take an infinitesimal chunk of current right here, I, we put a length dz, just listen, don't write, okay? We just do this. We go ahead and we assume that these rays are about parallel. There would be a slight difference in the length right here. We calculate the differential electric field from this differential current. Do you all follow me? This is the way you always do this. It's the building block approach. And I'll put that on the OneNote so you can look through it. You're going to find out that this thing really, you sort of flesh it. I don't ask you to recreate this. That's the reason I'm not spending a lot of time on this. What I ask you to do is to understand how to use the end results. Then after you have this differential current causing a differential field, you simply, which would be, just for the record, the differential electric field from this in the theta direction would be I that varies with the height z, right here. And it would be times dz over 4 pi. Then you would have the r prime, and this would be r prime. I'm just going to put this on here. You would have e to the minus j beta r prime, right there. Then you're going to have times, let me do it this way. Yeah, I can leave with 4 pi here. Then you would have the j eta beta right here. And then you would have the sine of theta in the a theta direction. That would be your differential field. Here, r prime would be put in terms of r, and this angle theta, which is this angle theta, which is this angle theta. And I'm not going to get into all this right here, but when you do it, the end result is you would take this and integrate it over the length or integrate it dz. After you turn the crank on this, and I'll put this proof up on OneNote. The end result is this is your electric field from an arbitrarily long dipole. Now the integration is a little clumsy because when you integrate this, the r prime right here actually becomes r right there minus, and then it's going to be beta z, all right? And it's going to be times, if you look at theta there, the cosine of theta. And that has to do with the difference in length here and here, but there's a beta, times z cosine theta, my bad. And when you plug this in here, then you're going to get a beta z cosine theta. And because beta z cosine theta, when theta is close to 0, it will become appreciable in terms of wavelength, and this integration becomes a little clumsy. That's the reason I don't do it. I'm going to put it up on OneNote so that everybody can look at it and see it, okay? You'll appreciate it much more if you look through the steps there. This is the end result. So if you have an arbitrarily long dipole, this is what you get for the E field. Now, a good question to think about since the test is coming up is, do you need to know that? No, you don't have to know that. Got that? I will provide that. The other thing I'm going to tell you is, like with any other far field, we're assuming this is just far field. R is much greater than L. H is just the E field divided by 8 and 9. and it would be in a different direction. Since E is in the theta, this will be in the phi direction. You all with me in this class? Just like a short dipole. The E and H are always perpendicular to the direction of propagation. It's propagating in R. So that's for an arbitrarily long dipole. That works. Some things to note about an arbitrarily long dipole is the impedance can go to near infinity. And the reason is if you look at this current here, somebody's going to say, well, how do you know that's the current? Well, the way they actually solve these things for current is really numerically. You can do these things where you take Maxwell's equations and you do what are called expansions on the actual differential equation in terms of approximate solutions. But ultimately, this is the one that's best describes it. The sine is a function you know. You don't know infinite series very well, but you know the sine function, right? Now take a look at this. What happens if the actual length right here is going to be lambda long? Just look for a second. Beta is 2 pi over lambda, right? I'll write it down. Just take a look for a second. We're going to assume that L is lambda. The length of the antenna is a full wavelength. Here's what would happen, by the way. You would get this, as far as the magnitude of the current, go to an absolute zero. You would get two humps there. And if you actually looked at the current, the actual current would do this. It would be positive in this direction. The negative going slope means it's going this way. Your full wavelength would be from here to here. But if you take a look at this and just look at beta times L over 2 minus the magnitude of Z, the beta L, well, beta is 2 pi over lambda, divided by 2 is pi L, minus, and 2 pi times magnitude of Z. Now just listen for a second. If you're at the center, this is pi, it's beta, 2 pi over lambda divided by 2 is pi, right? If you're at the center of that would have a lambda in it. If you're at the center of the antenna, Z is 0. So this term would be pi. Well, what is the sine of pi? What's the sine of 180 degrees? 0, right? The current is 0. That means for any voltage you drive it by, the current is 0, right? If I take V over I get infinity. You all follow me? Now in the real world, it doesn't actually go to infinity, but it goes to a really large value. And I posted some things about the current, both the real and imaginary part for dipoles of arbitrary length. I got to tell you one other thing, and it's not said in this book that way. Antennas don't have infinitesimally small diameters or radiuses. The actual driving point impedance of any kind of wire antenna is a function of the radius, and especially if the radius is of the order of 1/10 of a wavelength. Now, hear me on this one. You remember skin depth, right? Skin depth becomes a factor in the actual resistance, the actual heating of the antenna that would occur because of the resistance. There are other things. But in general, in Wentworth's book, he's assuming they're very thin and that this is a good approximation of the current. It is. The antenna will have a maximum impedance when it's any even number of wavelengths long. 1 wavelength long, 2 wavelengths, 3 wavelengths, and such. You'll get a huge impedance, which is tough, means you can't couple much power. You follow me on that? All right. Now, there's more to this, and I'm just going to say I don't want to spend a lot of time on this, but remember this, that the wire's radius plays a role in the actual driving point impedance, and whether it's a full wavelength or whatever it is. That's a general form for the electric field for any arbitrarily long dipole. There are reasons why you want a half-wave dipole. There's reasons why you want about a full-length dipole, and now we'll get into that later, probably. So the most common long dipole used is called a half-wave dipole. How many have heard of that? Half-wave dipole? Typically, when they talk about a half-wave dipole, they're saying the length of this antenna is a half-wavelength. Now, that's not really true, but let me go through that. If the dipole is a half-wavelength, when I look at this term right here, this is the formula for the actual, the electric field from an arbitrarily long one. That's beta L over 2, right? Well, beta is 2 pi, and I divide it by 2, I get pi, right? So pi times lambda over 2, the lambdas are canceled, and I get pi over 2, wouldn't I? Well, what's the cosine of pi over 2, a cosine of 90 degrees? It's 0, isn't it? This goes away. You follow me? Now, up here when I have beta L over 2, that's simply pi over 2. And here's what happens. That angular function reduces to just cosine of pi over 2 cosine of theta for a half-wave dipole. Make sure you know this. Write this down, start. Divided by the sine theta. Okay? We're going to talk about that pattern. That's the E field, and the H field is found by just taking the E field divided by 8 and 9. This is all far field, okay? Now, if you have that, a good question is how do you get the power? Well, you could take 1/2 the real part of E cross H conjugate, right? We'd find out that this angular form here would square itself, wouldn't it, class? We'd all find out what we'd get is also we'd have E would be 60 squared, and then it would be divided by 8 and 9, which is 120 pi, right? The j's would go away, the exponential, the e to the minus j to beta r would go away. And I didn't put this down, but let me just put down what the power is, radiated power density, or P average from this. And William, if you can find out where this is in your book, tell me, because it's going to be j, and I think the way he writes it is 15 pi. There's a lot of ways to write this. This would be the power radiated. Look for an arbitrarily long dipole, but it'll be for a halfway dipole too. It's not going to have a j, sorry. It's going to be 15 pi squared I naught squared over r squared. Then it's going to have cosine of pi over 2 times cosine of theta over the sine of theta squared in the AR direction. That's the power radiated, and
page 458, equation 8.8.
458?
Mm-hmm.
Oh, I'm sorry. Pi is downstairs. I'll tell you where this number comes from. If you take 60 squared, right there, divided by 8 and 9, multiplied by 1/2. Well, if I take a look at this, I got 60 squared, 60, 60 over 2, and this is 120, which is 2 times 60 times pi, right? And that goes to 30, 15. Isn't this just 15 pi down here? I think
It's 15 over pi r squared.
pi r squared, that's what. That should be pi r squared. This is right, what I've got here. But the way you get it is just take E, the magnitude of E, which is 60 over r squared. So you get 120 over a 60 squared over r squared. Divided by 8 and 9, you get 1 multiplied by 1/2. That's, you all follow me? I'm just taking 1/2 magnitude of E squared over R. Now, the interesting thing and the important thing is you see this cosine of pi over 2 sine squared? In Wentworth's book, he's going to call that f of theta. And that is really how the power is distributed in an angular fashion. This is really P normalized of theta. Now, it has, without, you can't just look at that and know, but if you work with it, you know. This will have a peak value of 1, and it occurs when theta is equal to 90 degrees. It has a value of 0 when theta is equal to 0. He shows us in the book. Lydia, are you looking at where this is plotted in the book, by the way?
No, I'm looking at page 466, which is the chart.
Okay, he's gonna, yeah, he shows the comparison between all of them. But this is for a half-wave dipole. Now, let me show you what that pattern looks like, because I'm trying to get at the essence of what you need to know. And I want to talk about things that are really, things that you take away from all this that you're going to use. And somebody asked me to do more examples. What I'm trying to do is show you the mathematics. I didn't do the proof because there's a couple of comments. But I want to show you mathematics of, applying this. So we're going to focus at half-wave dipoles. And something I'm going to tell you too on that is, when we talk about a half-wave dipole over here, I need to make this point. If you have a dipole that is exactly L over 2 long, and I mean exactly L over 2 long, it does have to do with the radius of the wire, but for now, this is pretty much standard. Then your actual input impedances or your input resistance is 73.2 ohms. You're going to see that somewhere in your text. If somebody sees this number, let me know. This is the real part. Do you see it, Lydia? Where do you see it?
It's
And what?
8.85.
I want to just star that. This isn't really true. This will vary 70 ohms, 69 ohms, up to about 74, depending on the length. If it's exactly halfway, it depends on the radius of the wire, all right? So it varies a little bit. Now here's what's always done, most of the time, 99.999% of the time. Listen. And his book, he mentions it. They don't use a dipole that's exactly lambda over 2, which would be 0.5 length. They cut it down, so the total length is about 4.8. In his book, he'll have 4.85 length. The reason they do is you get rid of the reactance. See that J42.5 there? If it's exactly a half-wave dipole, you're going to have a reactance also. So you're going to have 73.2 plus J42.5. Now that J42.5 doesn't radiate power. The only thing it does is limit current, right? So if you want a certain amount of power radiated, because the power radiated just comes from that radiation resistance, you have to increase the voltage, and that's at a cost. But if we just cut it down a little bit, the driving point impedance becomes strict real at about 72 ohms. Now in his book, he's going to have 73, something like that. It's really a little less. It's about 72, and it does vary somewhat on the radius of the wire. Follow me? Now, here, you get rid of the imaginary component. So now it takes the least possible amount of voltage to get the most possible power when it's cut just a little less, and there is no appreciable change in the electric field. Y'all hear me on that? And that's why if you ever build these, and I haven't done this, by the way, but I've always threatened to, get just a thin wire and a source voltage and measure the input impedance. You can do this very easy. All right, you'd measure the current voltage. You can do it with a network analyzer. You can do it a lot of these. And then take a pair of fingernail clippers or toenail clippers and start clipping off the end of that thing when it's on like a ruler. And you will see, I haven't done this, but I'm threatening to. You will see all of a sudden the driving point impedance go from about 72 plus J40 roughly down to just about 72 ohms. It's kind of interesting because there you know you've got something that it's for the frequency you're running is perfect. The other thing you can do is just put a dipole, half-wave dipole, drive it exactly at the frequency or half-wave dipole, and then start slowly decreasing the frequency a little so it looks shorter, and then all of a sudden the imaginary part will go away. You hear me on this? Anytime you see these half-wave dipoles, that's what they are. Now, a lot of times in the day when I was young, they would give you these antennas that were fold-out antennas. I don't know if you've ever seen these. What it is really a transmission line. It's 300 ohm transmission line or so, and you put it to the back of your receiver, and it would fold out. It was a folded dipole. That is not exactly half wave. Matter of fact, it varies somewhat. But what it'll do is, this is a twin line transmission line. It'll come up, and what will happen right here, it will go all the way around and come back, usually. Have you ever seen these or not? The fold-out antennas? Well, you guys are smart. You know that if this is an FM antenna, or an AM antenna, well, the frequency changes, right? So that isn't a half wavelength. But the thing is, over the range of frequencies, the FM is broadcast or AM. I'm not even sure if that's AM. That is roughly in the center band halfway loop. That's how they do that, all right? Just realize that. There's tricks that they use to do this, but I'm not going to spend much time on that. Okay, that's really the gist of the arbitrarily long dipole. The power radiated is there. If you got the E field, you got the power radiated. Just take the mag to the E field, square it. If you want the average power density of the point, and go ahead, once you have that, multiply by half and divide by 8 and out. But I never do that. You know what I do? Only thing I worry about with antennas is the radiation resistance and the gain. So the next logical thing you should be asking, okay, Dr. Budinsky, you've given us this. What about the directivity? Because if I have that, game over, right? If I got the radiation resistance and I got the directivity, I know the power pattern, don't I? Well, for a half-wave dipole, when you go about calculating this, put this down. It's different for arbitrarily long, but worry about the half-wave. When your length is about lambda over 2, or half wavelength, then the actual directivity, D, is equal to some D max, which is 1.64. That's about always the same. And then it's going to be times that angular function, so it's going to be cosine of pi over 2 cosine of theta over the sine of theta, and this whole thing squared. You all see that, class? That's the directivity. I'm going to do a problem with all this in it, because I've been asked to do problems, and I'm going to do one that showcases everything you would need to know. All right, sort of. Pretty much. All right, you got that, everybody? Now, that's directivity, which means, and here comes the bottom line, if we create a problem, and this problem is going to be made to exploit all this. By the way, we're missing Jack. How many people are we missing? Jake, you're here. Tyler's here. Ashley, Caitlin. We're missing some people, though. I know Jack's not here. Who else isn't here? I think that's about it. Is that right? Okay. I don't usually count heads, and I do not take attendance. And this, thankfully, we have lectures that are recorded, and we've got hidden notes, so we're pretty good shape. I guess people can get sick, but I don't know about it. Sometimes I'm the last person to know. All right, here comes a problem, and I thought about this. So this is like my classic problem that I give on exams. This type of problem, I'm going to explain. What I normally do is get a source voltage. Something like this. Just call it V naught. Let's assume it's at an angle 0, and the frequency will be F naught. Right? Then what I do is have a resistance here. I'll have a source resistance. With me? Now that's a typical source. Then I'll take that and I'll hook it up to an antenna. This antenna right here is going to be a half wave. So I'm going to say the length of this antenna is going to be, actually make it 0.485 lambda. Why did I choose that, people? Well, yeah, because what do I get rid of when I do that? The reactive impedance, right? Now it's just about 72 ohms, right, class? So I do that, so I make a little note to myself. Now Zn, the input resistance, is just R rad, and it's equal to 72 ohms. All right, I'm not going to try to trick you on any of these. That's the reason I made it 0.485. It's about that. In other words, it only has a real component. Got that? Now I come out here, and I'm going to say I'm at an angle theta equals 45 degrees. And now I'm going to be out at distance, this should look remotely familiar, R equals 10,000 meters. Now is it back there? See the head cone? And I know I've got enough time. Giving you enough time. Now I'm going to put an antenna up here. And this antenna This is going to be a length of lambda over 20. Okay? Hear me? So there's three things I want. First, I want the power density here. Then I want the E field. And then I want the power received. You all with me on this? So I want first the E, or the power, average power density at this point. We'll just call this point P. I want P av. Then I want the E field magnitude. And then I want the actual power received. And I'm going to show you some stuff. So first, I'll come back around here. How do you get P average? That's the average power density. What do I need to get that? In a nutshell, what would I need? The total radiated power, right? Then I have to divide that by 4 pi r squared, don't I? That's the average power density without any sharpening or any focusing, right? Then I have to multiply that by the
Directivity.
right. So now I'm gonna put it down, and I'm gonna answer the logical question. It's gonna say it's gonna be total power radiated, right, over 4 pi r squared. We have r. If you have calculators, you can do it. Can you read this okay? Then it's going to be times the gain, which is this, which would be 1.64 times the cosine of pi over 2 cosine. Now it's 45 degrees. I might as well put that in there. Over the sine of 45 degrees. And I got to square that. Let me put some more numbers down. Let me give RS a value of 50 ohms. Let me give V naught a value of 100 volts. Let me give F naught a frequency of 10 to the 9th hertz, low gigahertz, 1 gigahertz. And I know I've got R2 is 10,000. I'm not going to put that. Y'all with me so far what I've done? Yes?
I'm kind of confused.
Say again?
Where you have D right there equals 1.64, is that gain?
That's the max gain. This is max. All right, this is the angular function. You see, if you're going straight up when theta is 0, it's 0, isn't it? Because what? I mean, if you go straight up, you can't tell. And I'll get to what that looks like in a second, all right?
So that would be like if the efficiency is 1. You would
Yes,
use
yes.
that.
When I say gain, I'm assuming is equal to directivity because the efficiency equals 1. We can add efficiency changes. I could give you some with a certain radius and at a given frequency. You could calculate the resistance of that wire, and we could change the efficiency. For now, I want to focus on the actual main aspects of this problem, okay? But that's a good point. Yeah, I'm assuming directivity and gain are the same in this case. The efficiency is 1. It normally is very close to whenever you've got to mess up. That's one of those things you never want the directivity and gain to be any significant difference, because then you got a problem. Usually standing wave ratio is messed up. And I've had that happen. So getting back to this, if I look at this, well, I need the power radiated. So how do I get the power radiated, anybody? Want to try? What's the thing that really gives me the power radiated? P radiated is equal to 1/2 I naught squared times the radiation resistance, right? Radiation resistance we got, don't we? We need the current, don't we, class? How do I get the current? That would be the current flowing here. Anybody?
Wouldn't we just use Ohm's law since we have the voltage and the resistance?
We got 2 resistors in series, right? I don't have any reactance, thank God. Can I just take the voltage? This would be a peak value, 100, divided by that resistance, which 50 was the source, right? And I said that it's 72. So that would be the current, right? Are you with me? I'm always looking at eyes. Those masks are something. Now, I can't tell if you're laughing or crying. But, yeah? Did you want to say something? No, not you, Nathaniel?
Never mind.
That's 100 volts. I'm sorry if I didn't make it. So that would be the current. Now listen to me, all right? We got current, right? We got power radiated, right? Right there, right? You got that? You got R is 10,000, we square it, we get 10 to the 8th, right? We evaluate this angular function. Now, we can do this kind of silly. The sine of 45 is really what? 1 over square root of 2, isn't it, class? I know I'm going to square the whole thing. That's 1 over square root of 2. Now, the cosine of 45 is 1 over square root of 2, isn't it? 1 over square root of 2 times pi over 2. You would have to take the cosine of that and then divide it by 1 over square root of 2. But you can do this in your calculus. You with me? After you turn the crank, you can find out what the average power density at that point is. Correct, class? Remember the R squared there, right? Are you with me, everyone? If somebody wants to do this, William, do you have the ability?
Oh, yes, I can do it.
Do you have MATLAB or anything where you can just punch it? Or
I can just do it real quick in here.
if anybody can do this, I'd appreciate it. You'd be surprised how many mistakes are made right here. And this is the problem right there. A lot of times you work in degrees. 45 degrees is pi over 4 radians. So it's better to work everything in radians at this point if I give you the angle in radians. But if you want to work with degrees, make sure you know what you're doing, because here's the problem. That pi over 2 there is in radians, right? So you take the cosine of something, and then you got pi over 2, which is a radian measurement. Now, if you want to do it all in degrees, you don't need pi over 2, you need 90 there. You follow me on this, class? Okay, just make sure, because this is where problems are. So now that you have PF, we're going to assume you get this one. How do I get E? Well, I know I can get E because 1/2 the magnitude of E squared over A to naught is PF, right? That's my go-to formula. So I can get E by reverse engineering, can't I? There would be a square root of 2 A to naught times average power, which you've done in your last quiz. So it would be 2 A to naught times average power. I'm going to stop for a second. Okay? Not quite done. How do I get, y'all agree we can get E and we can get average power? Show of hands. I will give you, I'm not going to give you the gain of a short dipole. The short dipole is what? 1.5 sine squared of theta, correct, class? I'm going to give you the half-wave dipole. And the short dipole and the short, or the small loop have the same exact, I should say, directivity. Don't they, class? With me? So I'm not going to give you those. I'll give you the radiation resistance of the short dipole, and I always use radiation resistance to get my power radiated unless it's given. And then I use the directivity to get the power density in the E fields. I don't use the E field equation directly from the current, ever. All right?
I got PAV as 2.04 times 10 to the negative 8. And then
That would be watts per meter squared. Anybody confirm that out of curiosity?
PR I got 24.18.
Whoa. Before you do that, what did you get for E? Just multiply by 125 by 2 times 2. You take the root.
Yeah, sure.
I'll try to write bigger.
Question?
Yeah.
What is in the denominator of PAV? Is that d pi r squared?
Here?
Whenever.
That's some. Where?
P average.
Here.
Yeah, is that?
There's 4 pi r squared. Let me try to do it this way. This is going to be P rad over 4 pi r squared. Always think of it this way. Take the power density, assume it's isotropically distributed. This is what I always try to get to people, okay? Now, once you have the isotropic power density, what does the directivity or gain do? It sharpens it by the factor of the directivity. Go ahead, Kate. Did you have a question?
I got E. It's 6.01 times 10 to the negative 10.
10 to the negative 10?
Yes.
Is it really?
Wait, so it was P Ave times E naught times 2.
no,
All.
do P Ave, this is
Yeah.
10 to the minus 8.
Yeah, yeah.
All right, 2 times 10 to the minus 8 times 120 pi, right?
Yeah, yeah.
Times 2, that's
Yeah.
really what? 360 pi, about 1,000 times 10 to the minus 8 is going to be 10 to the minus, is going to be 10 to the minus 5 square root of that. No way. No way minus 10. No way. No way.
Yeah.
Just take 2 times 10 to the minus 8. Anybody.
Yeah.
Forget the over. Take that times 2. So that's 4 times 10 to the minus 8. Then multiply it by 120 pi. Right? After you do that, take the root of that. It's going to be of the order of minus 4.
Yeah, I got minus 5. Yeah, wait, let me see. Oh, sorry, I was using the wrong
It's all right. What do you
125
get, though?
equation.
Don't worry about it. You're going to make mistakes. That's why I want people to do it now. Trust me, if you don't do these calculations over and over again, you'll be amazed at how stupid you feel. 'Cause you can make mistakes.
0.0039.
Volts per meter. That's 3.9 millivolts per meter, which is reasonable. All right. What do you get for H out of the question? Just out of curiosity. You know it's going to be that divided by about 120 pi, right? Yeah, what do you get? Kind of eyeball it. Well, if you divide that by 1,000, right, you get
0.000, or you get 0.1 to the times 10 to the negative 3.
yeah, about that. But it's, I mean,
Wait.
you should have a few more significant digits.
Yeah.
Anybody give me H on that one? Tyler,
Okay, so it's
calculate.
1.04 times 10 to the negative 5.
And that would be amps per meter, okay? Now, I'm just putting this down there so we get the whole 9 yards, agree? With me? All right? Now, William, not you. How do I get P received? What's the equation, huh? Anybody? Well, didn't I say it's the aperture, right? You need how big it is, the area that power is incident on. And the aperture is lambda squared over 4 pi, right? Times the directivity, right? Well, the directivity is 1.64 times, and now it's going to be cosine of pi over 2 times the cosine of 45 degrees over the sine of 45 degrees. That whole thing squared. You're going to get tired of doing that, so you're going to store this somewhere usually. Y'all follow me? Now lambda, if I've got 10 to the 9th here, lambda would be C over F, or it would be 3 times 10 to the 8th over 10 to the 9th, or it would be 0.3 meters or 30 centimeters, right? So we take that and square it. That's going to be 0.09 divided by 4 pi, right? Times this is the area. But then what do? I have to multiply that by the average power density, right? To get the power received. Is everybody with me on this? Now somebody's going to ask, are you going to give us this, the gain, really, the aperture is equal to lambda squared over 4 pi times the directivity. I'm not going to give that to you. You're going to have to know that one. People are asking me about what formulas are available. I'm putting them up here one by one. That will not be available. That one you got to know. Matter of fact, I'm going to give you a list of formulas I'm going to supply sometime today. Okay? And you're going to find out, if you're familiar with this stuff, you're not even going to need. Well, you could need those formulas for halfway backbone, but in general, you're not going to need much at all. It'll be in your head. To get H for me, you should know how to do that. To get the average power density, you should know how to do that. Okay. Are you with me? What do you get for that answer, P received? mentioned you like examples in the application, so here we go. We're doing a lot at once, right? We're doing freeze, we got a half-wave dipole. Oh, I'm sorry, you know what? That ain't true. What did I mess up?
It's a directivity of the first one.
That's a that's a short dipole. That's the mistake. That wasn't done on purpose, by the way. Usually I do that on purpose. This was an accident. What's the directivity? Isn't that a short dipole right there? Right? The length is just lambda over 20, right? If that's a short dipole, then I know the gain is what? 1.5 times the sine squared of the angle, right? Now you'll notice I have that vertically oriented, so the angle here is the same thing as the angle here, it's 45 degrees. Do you all agree with this, class? So this would be the actual aperture, lambda squared times, or lambda squared over 4 pi, times the directivity of that antenna, and then it would be times the average power density. Do you all agree with that? I'm so sorry. You're going to find out there's not much difference if you use 1.64 times the other function. But what would you get for this when you do it? Remember, lambda is 0.3, so it's 0.3 squared, 0.09 over 4 pi, times 1.5, and it's 45 degrees. The sine of 45 is 1 over square root of 2, so it's divided by 2. So this should be, that's 3/2, that's 1/2, so it's 3/4 lambda squared right there, and it's lambda squared 0.09 over 4 pi, and the average power density, if that is correct, then would be times 2.04 times 10 to the minus 8. And you can give me that. I can't do that in my head very easily.
I got it.
Did you get home?
It's 1.10 times 10 to the negative 10.
That would be what? Does anybody else confirm that?
Yeah, I got it.
Guys? Jake? Did you get this?
Yeah, that's it.
All right, now that's nuance, but the progression is always average power density, right on target, and then it's multiplied by the area, and the area is lambda squared over 4 pi times the directivity, right? Now here's the thing, I had this thing aligned so that this angle and that angle are the same. The directivity is different because it's a short dipole. But what happens if I tilt that like this?
0.
It's 0, right? What happens if I tilt that like that?
1.
Then it would be 1.5 would be the directivity. The sine of that angle would be 90, which would be 1. Agreed, class? Let me show you one other thing. There's a lot of things I can show you. When we're talking about half-wave dipoles, or any dipole, a lot of times what they do is plot the normalized power pattern. So, let's break this down. This is going to be the power pattern. So what I'm going to do is just show you an antenna like this. What they normally do is plot it in spherical coordinates. But what they're going to do when they do this, they're going to have the antenna, I'm going to have the antenna at least up the z-axis, so it's aligned this way. Don't worry about the length of the antenna. And what they do is plot a radius vector where this vector r is actually equal to the normalized power density, okay? So if you look at the normalized power density for a short dipole, I know the normalized power density would be equal to simply sine squared of theta, right? We know the gain is 1.5 times that, but the normalized power density would just be sine squared. Do you all agree with that? For a short dipole. What would that look like? Well, it would look like this. where this would be Pn and this would be theta. Are you with me, everyone? And that is called the power pattern. They would say it would be the normalized gain pattern as well. You don't have to worry about any of this really, other than you all see how that was the normalized power pattern, right? Now if you wanted to know what the gain was, then you come out here, instead of having 1 out here, you just have this times d max, all right? And for a half-wave dipole, it would be 1.5, and that would occur right out here at 90 degrees. Are you with me? But it's a dumbbell. So what does the actual power pattern look like for a half-wave dipole? All right? Well, the normalized power pattern looks like the cosine squared of pi over 2 cosine of theta over the sine squared of theta. Believe me, I couldn't tell you what that looked like unless I plotted it. But I can figure out the way I normally plot things is I pick points at theta equals 0, if I can evaluate it, theta equals 45, theta equals 60, theta equals 90, and then I connect the points, and that's usually what I need to do. Well, for this one, what you're going to find is this. It looks very similar to this. The normalized power pattern looks like this. It's just inside that. The only difference is the peak gain is not 1.5, but actually if we took a gain calculation, it's 1.64. So they're very similar. Are you with me? Now both of these are low gain antennas. They're relatively unuseful for things like radar. Radar, you want real narrow beamless, you want all the power over a very limited range. That's sort of what goes on for those two. I want to mention one other thing before I move off this topic. Now there's something in general for any linked antenna and any type of antenna that happens. And the higher the gain, the bigger the problem, what I'm about to show you is. If you have an antenna, the maximum gain that the antenna has when it's a high gain antenna is called in the direction of the bore sight. You know, think about bore sight, think of the old movies where they had ships with all the cannons aimed. They went to actually bear their guns. The bore sight was where the cannons were pointed. It's their old military term. Well, if you have a high gain antenna, just say it's a dipole of length 30 lambda. That would be not really high gain, but higher gain. You get this. You're going to have one main lobe like this, and then you're going to have these lobes that are side lobes. All these are called side lobes. You don't want those. You'd like to get rid of them. And there's ways of suppressing them or minimizing them, but it's always at the cost of causing this main beam to get a little wider. There's ways of doing this, and this is more advanced antenna theory. But you realize this, high gain antennas, doesn't matter if it's a parabolic dish, it doesn't matter. A parabolic dish is pretty high gain. Doesn't matter what it is, you sprout these things. And those things are bad, and here's why. Suppose I'm using this as a radar, and I transmit energy. This is the power pattern and transmit. Hits something, reflects back, right? Well, the receiving pattern of an antenna is the same as the transmitting. So if the signal comes back this way, I'm going to get the aperture looks like lambda squared times the directivity right here, which is good. But if I watch this waveform and say it hits something higher up and it comes back and it hits this null, didn't show this, but then I get nothing. Worse yet, if it comes back and it hits this, it's coming in that direction from the target I splattered with what I thought was main lobe energy. Then I'm thinking the target's that way when actually it's at this azimuth. Now I'm going to spend more time with that. That's why side lobes are such a problem. We'll talk about that later, not today. So now, since I'm already 1 minute over, the test is Friday. The topical stuff is inclusive of everything we covered. We covered chapter 6, right? We're talking about wave propagation. We talked about striking surfaces normally and oblique, correct class? Any oblique, I asked you for TE or TM scattering at an oblique angle, I would give you the actual formulas for the Fresnel transmission or reflection coefficients. Is everybody, now you would have to know if it's TE or TM. Are you with me? but I will give you those. I do not expect you to memorize this. However, for normal incidents, you should know that the reflection coefficient is the impedance you're going into minus the impedance you came up from divided by the sum of the impedance you came from plus the impedance that you're going to. Are y'all with me on this? If I give you something with a shield, a certain thickness, and I ask how much is transmitted, you can assume it's thick so you don't have that multiple bounce pattern. You with me? You should be able to do that, okay? If I ask you for skin depth, you should be able to do that. I love this. I'm so thankful I've got you in this class because you write down this stuff and when people ask me, what did you say? There it is. I'm going to also say this, that if I gave you a wire of a certain length and I ask you for the DC resistance and then the AC resistance, you hear me now? You should be able to tell me the difference. That means you have to know how to use skin depth to calculate the change in resistance. You with me? Right? Because skin depth limits the current to the surface of the wire. If I give you something where I ask, by the way, with the shields for how much power or E field is transmitted, either one. Or reflected for that matter. If I ask you for, just listen, if I ask you for waveguides, remember the problem with waveguide where you have a load and a certain length of waveguide, how to get beta in the guide, right? Remember how important that was. I will give you that crazy equation that the input impedance for like a transmission line was Z naught times the quantity ZL plus J, right? Times Z naught tangent of beta L. It would be lossless or very low loss. Beta times L, that's beta in the guide over Z naught plus J ZL tangent of beta in the guide times length. You with me on that? So I'll give you that. I'll give like the problems we did. You don't have to worry, but you got to know how to do the calculations. Hint. So make sure you run the calculations through a few times and you know what to do. With waveguides, I'm not going to give you fiber optic questions. The reason I choose not to is the book dabbles with that. There's no real in-depth treatment. We don't do cylindrical waveguides. If we did, you would get a problem. But you're not going to get there. Now, with Chapter 8 material, we've got wavelength, right, which we had in Chapter 6. We're going to have that. We're going to have power radiated. We're going to have gain, possibly, right, or directivity. We're going to have the standard short dipole, small loop, half-wave dipole. Don't worry about arbitrarily long dipoles, all right? Half-wave dipole, power received, right? Just like that. Now, I haven't gotten to arrays yet. My next topical thing is going to be arrays and power received there and then radar. That's coming up after this exam. So does anybody, and consider this my office hour, have any specific questions related to the exam material or anything for the betterment of the class, for the best interest of the class?
The problem we just did was a long dipole, wasn't it?
What's that?
The problem we just did, it was for an arbitrary long.
No. That was in the beginning. I said this is the E field. It was a half wave dipole, wasn't it?
Okay.
And then it was a short dipole. Just look. Here I said it's 0.485. The reason I did that, the E fields will be the same as if it was a half wavelength
Okay.
in H, but the difference is you only have a real component of resistance, the input impedance. That was the key.
Yeah.
And I don't like trying to trick you with.
Will you be writing the table on page 466 for
No,
us?
I will give you the half wave, right? And I'll give you the radiation resistance of the small loop, but I won't give you the radiation resistance. Well, and tell you what, I'll give you the radiation resistance of the short dipole. But I'm not going to give you the gain of the short dipole. I'll give you the gain of the half wave. How's that? Because that's a weird formula. And Caitlin, if you could just send me an email telling me, here's the stuff I've got down, or is there anything more? I will add to that, and I will give you a formula list that you need to know. Fair enough? I will give you the formulas I provide. You will provide your own formula, I mean, in your mind, what you're gonna need to know. Because if I show you what I'm providing you, then you can figure out what you need to know. But it's, if you've done the problem, all the problems, then you should be prepared. One other thing, last thing I'm gonna say, and I say this, I really, at some point, I think I just need to stop this, but I'm gonna try it again. Get your sleep. This is an analytic text. You have to be an analytic, you have to be able to think well. You can't just cram and come in on speed and expect to score high, because people flip out, they always get confused. Get your sleep. Don't get jacked up and try to relax. It's not meant to be a difficult, stressed event. It's meant to be an event that actually probes your knowledge base. So please come in a somewhat relaxed environment, get your sleep. That's about as best I can. There's nothing I can say to make people do this. It seems cramming is part of the rite of passage. I never really crammed. Matter of fact, what I did is about 10:30, 11 o'clock. I was getting up at 6:37. I just watch TV, play ping pong, anything to get my mind off, go to bed. If I know it, I know it. If I don't, I don't. Staying up till 5 in the morning is not going to do you any good. It does on a history exam, and I know that. But it's not on this one, because you got to think analytically, and that's what's hard. Yeah.
Can we ask you how many problems there are going to be?
Oh boy, I get this one through. There's going to be 4 pages with special, each with different problems. However, there will be multiple parts to each problem. I mean, I'm going to ask you, just like I did here. I want average power density, EH, power received. If you take a look at my quizzes, and just take a look at what I do. It's usually one concept, right? 3 or 4 parts I want to answer. Okay. Fair enough? How many had me before? I know you have. You? Oh yeah.